analysis in a different way. It was due to an impurity of praseodymium. It was excited by the protons that gave a gamma ray line that no one knew about before that just happened to be where the element 126 X-ray line would be. Well, this didn't knock down the superheavy elements entirely, it just meant that what they did was wrong. So what we decided to do, somewhat a little later, just within a few months of this, we decided that we had not found the elements in the usual way. Let's try something a little bit better. And taking all the technology we had, we decided to take curium-248, which is a heavy isotope of curium that is available in the laboratory, and bombard it with calcium-48. Calcium-48 occurs in your bones. It's very tiny quantities, 1 part in 2,000 or so. In order to separate it, it's cost something like $100,000 a gram, so it's kind of expensive. But we had enough of it that had been purified at Oak Ridge, and we had the super highlight. By this time we had the super highlight, the machine up there in the second photograph on the right. We decided to do a really nice experiment. So we had a collaboration between Livermore and Berkeley. Livermore made this very fine target, and we supplied the wherewithal to do it in the accelerator. And we started bombarding it. Well, now we did this in a little bit different fashion than we had before. The easiest way to show this to the transparency. Oh, it's got a piece of paper. Okay, there we go. It's a very simple experiment. Here's the calcium-48 beam coming in. These are all, this is very expanded scale, hanging target, and we call it come out in this direction and stop in aluminum foils. There were a series of aluminum foils that were mounted on little rings. Okay, so the idea was to bombard it for a period of time, and then take it out and dissolve it in the feature. Add tracer at this point, mroe 241 tracer. So what you would have in solution would be the actinides, the super heavies, and the mroe 241 tracer. But it was noticed that what is this strange blackish crud that's floating on the surface? They had noticed on these foils there was kind of brownish material on them, and people wondered what that was. They said, well, probably carbon. Well, where did that come from? In any event, this was the first thing that was going to solve it. Then, next thing was to do a little more chemistry. And here it shows the regular superflux was called the super heavy element fraction. It was mounted on after the chemistry, mounted on a foil, and counted it with a semiconductor detector, and counted for alphas and spontaneous counts. And there were no SF counts at all to begin with. And the other one was since people said, gee, that blackish crud, if that is carbon, that's a noble element, essentially, and the noble elements like gold and super heavies would stick to it. Indeed, they found X-rays when they looked at carbon by itself, the X-rays had said that this is gold X-ray activity. So, the idea was that if that's noble, element 116, which is the compound nucleus, would also be noble. And it would stick to carbon. It's just simple chemistry. And that's what you'd expect. So Otto, who was the team captain here, said, let's take that carbon fraction, which we filtered off with a piece of paper, and mount it in another detector and see if there are any spontaneous fissions in there, just in case. So that was done. And here was the semiconductor detector, and here's the carbon foil, and here is the carbon in the filter paper, and here is what happened. This carbon fraction had a few spontaneous fissions per hour. When the first one came in, we were really bowled over. Whereas in the normal regular super heavy, there was nothing. And now the last fraction, the actinide, with all the material that was known to be actinide, was put on a big filter paper and put in another counter, not a proportional counter here, not a semiconductor tank, but a gas counter. because it was fairly large. It was just simple. Happened to be a counter that I had up in Thailand. So that was counted for a while, and it had about the same amount of fission activity as the carbon traction. But it had all of the tracer. Now here's a classical case where the tracer went one way and this unknown activity went with it. And the other case, with no tracer and about the same amount of fission activity. It sounded like super heavies to everybody. And Seaborgium especially was really convinced by that. He said this has a pretty good chance of being super heavy elements. So now, what do we do next? Well, all you can do in a case like this is to follow decay on these activities and see what happens to them. Do they decay differently? Did something else happen? So that was done, essentially. The counter we can do the work after that. And people like Mike Nishkin and myself who worked on the accelerator part of it, and got it going, were kind of worn out because we worked for days getting everything ready. And everyone just left. My wife and I went to Point Reyes to do some birding. That's the way I used to relax in those days, with the birds. And what we found was kind of interesting. At the end of the day, I called back to the laboratory and talked to Glenn Seaborg about what had happened to the decays. He says, well, it's very interesting. He says that the ratio of these two activities is still about 1:1, and they're decaying at roughly the same rate. It sure looks like super heavies to me. So that was the status for a while. That evening, though, something bothered me about the experiment. I didn't know what it was. But I went up to the laboratory and I examined the counter data to see if everything was all right. Well, it looked okay. But I went one step further and analyzed the pulse spectrum of this particular this fraction. This is the actinide fraction. Now, what it looked like was a screen curve. And the threshold for counting spontaneous fissions was something like this. So obviously we were missing most of the fissions. It should have looked like this, you see. But it did not. Okay, what does that mean? Well, there's nothing more I can do about it once I've known that, but I didn't know what it meant. So I went home, got into bed. I was really tired. Everything's fine. So I woke up about 6 o'clock in the morning with a terrible nightmare. I've never had this happen to me before. I dreamt that I was driving a car, and I came across another car with a bunch of Russians in it. And I was not going to allow them to get ahead of me. I have a faster car. So I started speeding up, but I couldn't pass them on the left because of the traffic. So I tried passing on the right. You know, that's scary. So I noted as a fast driver. So I did that all right. I passed them on the right, and everything was fine. I went over the shoulder, and all of a sudden, here was a brick wall coming up to hit me. Just like that. So I tried to put the brakes on. The brakes didn't work. They were out of control. And then I woke up. It's a terrible dream. This was just really quite dramatic. So I got in the shower and said, what did this mean? So let me I'll read what I wrote. At this point, I woke up. Out of control. In the shower, I reviewed the dream because it had been so terrifyingly real. I realized it had been prompted by yesterday's big super heavy element run that was still being counted. The mind is a wonderful thing. Symbolism was especially acute, complete with the race for the Russians to find the super heavy element first. It had come to the conclusion that the experiment was out of control. Now it was up to me to figure out why, and suddenly I understood what had happened. The fact that we could see the dark red meant that the thickness was of the order of 10 micrograms per square centimeter. And this meant that roughly these carbonaceous films were 5 to 10% as thick as the aluminum foils that had been dissolved. So the same fraction of the recoils would stop in those layers. If that material was not capable of being dissolved, then neither would the actinide recoil atoms lodged inside it be dissolved, and neither would the tracer penetrate the films. We had not performed any chemistry on these atoms at all. I decided that the source of the carbonaceous crud was most likely the organic binder, and using the silver paint that had been used to fasten the foils to the rings. I knew that the beam was depositing about 100 watts of the probe during the bombardment, so it would become very hot. It was very likely that the binder would be vaporized and end up as carbon on the aluminum foils. Whether the carbon was deposited immediately or slowly over the course of the bombardment, I could not know, but within a factor or two, it seemed like a very reasonable scenario. So I went up to the lab to confirm it. Shortly after I arrived and checked the equipment, found nothing that disagreed with this hypothesis. Glenn Seaborg called on the phone to see how the superheavy element fraction was doing. It must have taken me at least 5 minutes to convince him that it was a false alarm. But finally, and very reluctantly, he accepted my explanation. Shortly after that, Otto called up. But it took me 10 to 15 minutes to persuade him that superheavy elements had vanished. I really felt bad for having to be delivered with sad news after having discovered the superheavies for all of 18 hours. In retrospect, it was an interesting experience, even though very disappointing. We prepared very well, according to the technology of the times. We'd overcome many obstacles just to make the excellent embarkments. We had performed the experiment with professional expertise. We had made an acute observation during the experiment which should have led us to discover the superheavies. And finally, we had chemically separated what could well have been a member of that tribe. Everything was perfect, except for that last statement. There was no superheavy element candidate. We had been misled by an amazing and also amusing artifact of the experiment. That actually happened that way. And it was really pretty amazing, very disappointing, but fortunately we never published anything, of course. This all happened over a period of 24 hours. But occasionally, this sort of thing can happen when you're doing something that's pretty darn important and you desperately want it to be true. But sometimes people even use body English to make it seem that it is true, and that's a bad precedent to try to do, because you're going to get in trouble if you're trying to do that. Fortunately, in all of the experiments that we had done, we had made a few mistakes, but they had been corrected ultimately. In the early days of finding elements 102, 103, 104, 105, even 106. There were disagreements with the Russian team. They were very good scientists, but they didn't have the experience nor some of the technology that we had, and so they were not able to do the same things until later on. Later on, they pursued their science and did quite well, and have done some very, very good things with their experiments. But it's been a wonderful experience for me to be in this field for so long, and I'm really sorry that Glenn Seaborg can't be here. He would have jumped up and down with joy to see the super heavy element experiment that was put together in the radiation cyclotron, which was successful, and it will undoubtedly lead to other experiments in this field. This will meant the last experiment, last result we've done. There are probably at least a half a dozen more to be obtained. There's a lot of work, but I think it'll be done. And as far as the science is concerned, it's really a pretty fantastic thing for young people to get into a field which had matured and people thought everything had been discovered, but all of a sudden we have something to do to work with. And it's really, really fun to expose this and say, now your turn. Just a simple experiment like proving element 102 is a rare gas. How do you do that when its half-life is only a quarter of a millisecond? So there are a lot of challenges, and we'll keep on working. Thank you.
Thank you very much, Al, for a very interesting story and insight into some of the past history of superheavy element work. as Al has mentioned to you, of the many transcurium elements, one